Okay, so today we're going to move on to kind of a new concept, I guess we will call it, in that how do we design circuits that remember? How to design circuits with memory, right? Because up till now, everything we've done is combinational, which really is meaning the outputs depend solely on the combination of the inputs. Circuits with memory we call sequential, which because they remember what came before in the sequence, right? So we're going to start talking about how do we design sequential logic starting from combinational logic blocks, right? Because we're going to use the same circuits that we've done before, but we're going to do it in kind of a clever way. So the first thing that we're going to do is set up a couple of NOR gates. And we're going to set up, well, if you know what Ouroboros is, which would be a great question on the exam to see if you're reading the instructions, because I'm sure most of you don't, right? It's the snake that swallows its own tail, goes on forever, is we're just going to set up a situation where the information can chase its own tail, right? That will help us remember what's happening. So we're going to do what we would also call cross-coupling, like this. Now we can have information that just kind of stays there. And I'm going to call this signal S and this signal R. And then we're going to see what actually happens to these NOR gates, right? And to do that, it turns out it's really helpful to start off just explicitly writing out what is the truth table for a NOR gate. So the NOR gate, right, an OR gate would have a 0, 1, 1, 1. So a NOR gate is 1, 0, 0, 0, right? That's NOR. So now I can go ahead and make an assumption about what is S doing and what is R doing. And what I'm going to do, because it turns out to be much easier, is if I set S to 1 and R to 0 to start. So I'm going to rename these from A to B, and I'm going to say this is S, this is R. Okay. So if S is 1, the output of this OR gate has to be 0, right? Because if either of them is 1, the output is 0, so F is 1. The output here is 0. So then that 0 comes back around, and I already have the 0 here. So I've got a 0, 0, which is 1. Okay, so now we're going to do the situation. So this is just the NOR gate, and we're going to now talk about this as the circuit overall, and I'm going to call this L. Actually, I'll start with what it actually is. And I'm going to call this output signal Q. I'm going to care about this one for now, okay? So in the case of Q, if I have S is 1, R is 0, 1, 0, I get Q is 1. All right, what happens if I flip that? If I have a 0 and a 1 here. Okay, well, in the case of that, we have a 1, which means any 1 means Q is 0. So R is 0. There we go. And now, what happens if I change this 1 from 1 to 0? Actually, we're going to do this the other way, because those two are base conditions, right? Either I am just having S or just having R. But things are going to behave a little bit differently depending on the combination of them being both true or both false. And now let's look at that situation. And the easiest way to do that turns out to be starting from S is 1, R is 0, staying with R is 0, but transitioning to S is 0. Okay. So when I do that, S is changed from 1 to 0. So this changes from, well, this was 1, so this is going 0. Right? Because if a 1 makes a 0, this is a 1 to something. Well, I've already set this signal around that was a 0. And so I have a 0, 0, which means 1. Stays 1. Now this one is not quite going to be true because it turns out if I go the other way and it starts at 0, it's going to stay 0. It turns out that it stays what it was. And you can go ahead and chase it. So this one, right, 0 was 0, stays 0. Because this was 1, it feeds back around, right? Whereas if I'm now 0 here, 0 here, I have to erase, right? Because we have to reset from the concept unless I want a whole bunch of slashes as I transition. So now we can do the situation that we knew where set was 0 and reset. Spoilers. Set, reset, SR. Reason I chose those. So now set was 0, reset was 1, which meant that Q was 0. Well, if I transition from 0, initially the 0 got passed around. 0, 0 meant this was 1. A 1 gets passed around, which means the output is 0. It stayed 0. Nothing happened. Okay, so in the case where I am neither having S or R, it's not 1. It turns out that I need a new kind of notation, which is to say my next Q, Qn plus 1, is my old Q. It stays, it remembers what it was, which is really quite convenient. There is, however, a bit of a problem in that we can now say that R is reset, which is to take the Q output and tell it to be 0, reset to 0. S is set, it makes the output 1. If I neither set or reset, I remember. What happens if I am attempting to tell a signal to be both 0 and 1? It's problematic, right? It's not really going to work. Well, nothing in this intrinsically is the end of the world. If we looked at that, if we went 1, 1, well then here a 1 means this has to be 0. The 0 feeds around. I have a 1 here, and I have a 0, 1. Means a 1, I have a 0 here. Okay, so this is now 0, 1, 0, 1. It works, and it turns out that this is looking like it's going to be 0, probably. The issue is that we've already talked about how these devices aren't ideal. And so when I tell it to set and reset at the same time, I can miss, right? It might not assert at the same time. So what can happen is it can start chasing its own tail, alternating 0, 1 really fast. It can do what we call oscillating. So if we set and reset at the same time, that's bad. So we don't do this. We don't set and reset at the same time in this device, which is called an S, I guess I can write it over the truth table, an SR latch. Now I'm going to warn you, I'm going to mess up this all the time. You're going to hear me slip up and call it a flip-flop. It's not yet. We'll learn shortly what a flip-flop is, which they're related to latches. So be vigilant. Until I define flip-flop, if I say flip-flop, I really mean latch, and I apologize. I'm going to be really careful. But this is an SR latch, which just means I can reset it, set it, or latch onto the old value. I can hold what it used to be, which is an incredibly useful little bit of technology. Right now, we can start to remember something. We can draw this device. We give it a schematic symbol, write a block diagram, because we don't want to draw this all the time if I don't have to. So draw a square, one input S, one set R, Q. Turns out this signal is always supposed to be the opposite of Q, and it will be as long as I don't violate this. So this is not Q or Q bar. That's my SR latch. We know this because it has the letters S and R in it. We can have active low. So it turns out if we build the same circuit out of NAND gates, it works out really well as the same, essentially, except for the inputs are active low. Yes.
Is this essentially like how RAM works, or is this?
Yes, we're actually building towards how something like NOR flash RAM would work, is what we're building towards kind of. These are more of what's called registers, which are your temporary memory. This is how your temporary memory is going to be built. The things that you don't want large storage for necessarily, but you want quick access to. We'll talk we'll talk more about the actual how we build something like complex memory, like real NOR flash, NAND flash in digital systems. Okay. So now, but this one does have some issues because, well, the 1-1 is one issue, right? If we assert both of them at the same time. And we're going to want some other designs, but I want to point out that if I design this with NAND, we can have active low signals. If I want to indicate that they're active low, I can say, bubble, bubble, that is now an active low input SR latch. Okay. SR latches have some really cool, useful applications. So one of them is you have the potential when you're interfacing to a real world circuit, okay, that if I push a button, we would like to think, right, your FPGA, they have little buttons or the switches that you'd like to think that when you push it, it goes on. But that's not what happens because it's a real mechanical device. Unless you're very carefully designed, what really happens is it goes on. So if you're, say, trying to count the number of pushes that you did, each push might be 3 to 7, right? So now you're not sure what you're doing. Turns out the SR latch can help with this problem. It's not perfect, but if I have a switch, and I'm going to draw it like a button just to make it clear, right? So that's a nice button schematic. And then if you push here, it contacts and completes the wire. It's a button, it goes ting, 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 and it ends up with an issue. However, if I plug that into something that counted, I'm going to have a problem. So what I want to do is leverage the SR latch and I'm going to pair up them. This is just one way to do it. Okay, so here I'm going to introduce a new component that you will encounter eventually in your career, which is a switch that is not just on or off, it's in one of two locations. This is called a single pole double throw. Single pole meaning it's one thing that I move, and double throw meaning there's two positions that it can connect to. So the on or off switches are single pole, single throw. They're connected or they're not. Single pole double throw can go one to two locations. So now when I throw my switch and it connects to set, so I'm sending a 1, instead of going 1, disconnect, what it's doing is now going, well, it's connecting to ground. So we probably would want active low here technically, but it's okay. And what's going to happen, right, is it's going to go set. But guess what? If I set multiple times in a row, it's still just 1. The output will just go 1, 1, 1, 1, 1, 1 as it bounces. So the bounce doesn't matter. It no longer has a problem with the bounce, fixed by just that simple circuit. Now this doesn't quite help us because now this is only going to track if I reset it manually, right? Because once I've set it, it's going to say 1. So if I want to reset the count, then I have to intentionally go back to R, which is going to do the same thing, which is going to go reset, and just go 0, 0, 0. But the bounce of the switch now no longer is going to toggle on and off like our initial design would have. So we're going to build up an even bigger, more complicated circuit slowly that's going to get us to debouncing a switch, which is going to be like, what if we really do just want to count it go on and then off, and we just want it to release? And that's where we're going to slowly kind of build towards with these devices. So the next step in complexity is, well, it's nice to have set and reset, but it's also nice to have something that's just going to hold on to data, right? Some value of a data signal, which is this, we have to keep track of a set and reset. What do we do if we only want to keep track of what was the output of my signal last, right? What was my last signal? Well, we do that with something called a D latch that starts out with an SR latch. And we just add a little bit of circuitry to it. And let's start with active lows here because they're NAND gates, because this is gonna make it easy. All right, so now this is a D latch, all this combined. But let's talk about what's happening with it. So the first thing that I'm going to do is I'm going to simplify by being, okay, well, we want to use universal gates because they're size optimal, right? They're easy and cheap to design. So if I want to start with that, then I can just cancel out these bubbles, right? I can know that inside they're all NAND gates, but I'm going to simplify the drawing because it makes it just a little bit easier to talk about. So cancel the two inversion bubbles. And I have AND gates, which are really easiest for us to talk about what does an AND gate do, right? But it doesn't change the functionality. We understand that it's still universal gates. I've just drawn an equivalent circuit. So the first thing that we'll notice is if EN, enable, is 0, what does that do to these signals that I'm going to call A and B? If enable is 0, can A and B ever change? No, they're 0. If enable is off, they're both off. Meaning, I will never set or reset if enable is 0, which is nice. So that also means that if I'm not enabled, I am just remembering what my last value was. Now, if D is 0, that puts a 0 puts a 0 here, 0 here. So let's assume that enable is 1, 0, we're not setting, but if D is 0, then there's a 1 that comes through here, passes, and resets. Okay. So now we're inverting, unfortunately, at this point, right? Because if I have a 0 here, I get a 0 here, I'm not setting. So well, it's okay. I can then just call my output Q and Q bar active low, and everything's fine. Or I could invert the way the inverter is going. Similarly, if I put a 1 here, I get a 1 here. Right, did I do that wrong? I'm so foolish. I'm wrong. We're okay. We don't need active lows. Helps if I write down the numbers. Let's start with 0. Means 0, not setting. 0 makes a 1. Enable is 1, makes a 1. We reset. Q is 0. If D changes to 1, enable stays 1. This output goes to 1. This output goes to 0. I'm no longer resetting. I am now setting. That becomes a 1. My D flip-flop, D latch just follows data if I'm enabled. So now if I want to keep remembering something, I just set enable to 0. And if I want to update it, I set enable to 1. Okay, so where are there? I'm going to come over here and just redraw it, basically, which is a way of saying that I have D, I'm just going to flip them, enable and D. And this is my next Q, my next output, okay? Well, if enable is 0, it doesn't matter what D is doing. We just remember the old value, right? It holds on. If enable is on, then it just follows D. That's a D latch. Again, it's just latching on to whatever the data input is, the input. So we're going to look at a lot of timing diagrams for this latch section. That's going to be the homework, really, is mostly timing diagrams. So let's say that we have a D input and we have an enable input. That does this. Okay, and just to make it a little bit obvious where each of these transitions are, I'm going to add some dashed lines. Okay, well, in the beginning, if this is Q, if enable is high, that means I'm following data. So data is 0. Well, at this point in time, D changes, so Q just follows, right? So we're still enabled. Then enable turns off here. That means that until enable turns on, Q won't change because it's not enabled. So this D goes to 0, nothing happens. Well, now the enable turns on here, which means it's going to get a little blip of a 0 before the D pops back up, starts coming over, the enable turns off. Doesn't matter that the D changed. So I'm just looking at follow D. Q follows D when enable is true, otherwise holds its value. So what you want to do in a timing diagram like this is go identify the locations where something changes. And it would be really good if I had the full swath of colors, right? Because then I could be like, well, here's another interesting point. That's an interesting point. And that's an interesting point. And now I have the blues, which is where D changes, and the greens, which is where enable changes. And those are the only places where Q is going to change. And in fact, Q is only going to change if enable is true. Okay, now, as always, we have to add one more layer of complexity to things, right? And the reason is that if you think about any of the computers that you deal with, right? If you go out and buy a computer, it's going to tell you that it has some 5 gigahertz clock or whatever it happens to be. That clock is a signal that is designed to keep things timed together. It's for what we call synchronous design, meaning that we want to know that whatever operations are happening, whatever math we're doing, for example, is being done at a specific time. How do we synchronize these operations? How do we keep them going together? And the answer is a thing called a clock. Clock is a signal that just goes 0, 1. Poorly drawn.
It's a castle.
Oh yeah, castle. Yeah, this is all a clock is. Now the clock can be described in 2 different ways. One is the time between 2 of the rising edges or 2 of the falling edges. Basically, what is its period? How often does it repeat? And we call that T. It is related to how often this happens, how many times per second, which is hertz. And we call that frequency, which is equal to 1 divided by the period. Simple relationship, easy to look at. So frequency is usually what we talk about as engineers. Frequency is how many times per second. The unit again is hertz, abbreviated HZ. The units of that are technically 1 per second, which is just how many times per second does this happen. And so if you have a 100 megahertz clock, that means it happens 100 million times per second. There's 100 million rising edges every second. Okay. So in order to do this, to do something with this, I need a circuit that responds to these edges, right? That's what's telling me do an operation, do an operation, do an operation. Do one thing, now do it, right? That's the synchronization. And it turns out it's fairly easy to design one of these using the latches. And this is going to be my enable Q. I don't need my Q bar in this case. And again, this is input. I'm just going to call it data, but I'm going to then call my other signal clock. I'm going to wire it up like so. So now let's go look at what happens when I change these signals. Okay. So we're going to, again, use a timing diagram, and I'm going to draw clock. In fact, it's probably better if I expand this and make a little bit slower clock just to make it easier for me to draw. 2, 1, 2. Okay. And now this is going to be clock. This is going to be D. So let's not call it, well, yeah, D is fine. And then call the intermediate one alpha, and then I'll call the output Q. So then D here, I can actually, maybe I'll use an example here. Start low. Let's do that. Okay, so in the case of alpha, there's an inverter. So if clock is 0, alpha can just follow D. Okay, because of this inversion. So when D is 0 and clock is 0, alpha follows D. So it's going to start at 0. And then because clock goes high, which is our enable signal that gets inverted, it can no longer follow. So nothing happens. In fact, nothing can happen on that line until here when we turn back on our enable. At which point D is high, so it can step up. And I'm going to use a little bit of a delay just to offset it because it's going to help us visualize things in a second. Follows D, clock goes high, nothing can happen until we turn back on our enable, turn our enable, D goes to 0, D goes back to 1. Here, where we turn off the circuit again, turn off the enable, it's frozen at 1. Here, we turn it back on, still 1, turn it off, still 1. Here, you can follow. Okay, so that's alpha. Is I'm just looking at, is it enabled or not? Okay, well, now let's look at clock 1 being on instead of clock 0 being on, right? And we're going to follow alpha. So we'll go grab, let's see if this black works. That'd be really good. Nope. So now, well, alpha kind of has this interesting issue where for Q, unless I make an assumption about Q at the beginning, I don't know what it is, right? Because I don't have a time before here. So Q is, I don't know at this point because it's not enabled. However, finally, when it comes and gets turned on here, then it can start following alpha, which is to say 0. And this transition happens just a little bit after the clock changes, so it's not going to see it happen, right? That's why I did this offset, is so that I don't run into this weird issue. It's still 0. Here's where I turn back on. Alpha is 1, so I can turn on. Here it turns off. It's still 1 because this transition happens just a little bit after, right? There's a little bit of a delay because of the gate. They're not ideal. We're off. Here we can turn back on. Still 1. Off. You can start following again. Still 1. Turns back off. The transition happens a little bit after, so still 1. Okay, that's the timing diagram. These are a little bit tricky, and it is made much easier by doing slight offsets between the transition and the time that things happen, because otherwise you have to start asking yourself, what happens when I enable a signal at the exact same time as I change that signal? And the answer is we don't know. If I ever do that in real life this close, it's actually going to break the circuit and it's not going to work right. In an ideal circuit, it would do something, but we know that no circuits are ideal. So just be aware of that we have an issue that we need to make sure that we've changed the signal sufficiently before I enable or disable. And we call that the time before the clock that I have set up the signal is the setup time, TSU. Setup time. That is the amount of time that a specific device is required to have its input stable before the clock changes. Similarly, the time afterwards is T sub H, T hold time, because I have to hold it afterwards. And the reason is pretty simple. So I draw my clock like this, right? But that's not what's really quite happening. If we were to zoom in, the clock would do something like this, right? It doesn't have a perfect transition. Nothing happens instantly in the real world. So there's some transition time. So if this is clock, this is D, and D changes at the quote unquote same time as this, from 0 to 1. Well, at some point in time, the device is going to decide that this clock is 1 instead of 0. And at some point in time, the other device is going to decide that D is 1 instead of 0. But that time is not going to be the same amount of time. When does it change, right? So is it going to take the 0 or the 1? We don't know. That's what we call a timing violation. So we need to set up the signal and hold the signal for a specific amount of time. And It's just in your data sheet. If you were to pull up the data sheets, right, that you use to figure out what pins are connected where to the logic devices that you've built on breadboards, guess what? They're going to have a setup and hold time. And if you violate that kind of thing, then you're going to have weird abnormal behavior. And we could go and grab exactly this type of device. We have latches downstairs in the cabinet that we could go and build fairly sophisticated circuits. I'm not going to do that to you. We're going to do everything in VHDL because it's more practical. But we want you to understand what these devices are doing. So this device is called a D flip-flop. And what's cool about it is I've drawn the timing, but I haven't pointed out the nifty part, which is it only cares about the value of D when the rising edge happens. So if you look at this, it should be 0, 1, 1, 1. 0 transitions to 1, 1, 1. It completely ignores any weird little blips that are happening to the D input signal. That's the nice thing with these D flip-flops is now I have combined 2 D latches to build a D flip-flop that will react only to the rising edge. That being said, I could just as easily design a device that responded to the falling edge. I could do that as well. It turns out in VHDL, it's very easy to accidentally design a device that responds to both the rising or the falling edge, and we generally don't like that. So stick to one. And we'll talk about the VHDL. How do we design these devices in code? Now, I guess, actually would be a really good time. Oh, and this, when we combine them in this type of architecture, we redraw it as a D flip-flop, which has a D, and then a little flag looking symbol, like a little pinion flag, that this means there's a clock input. This is a clock's input. That's all that symbol means. And then it has a Q and Q bar output. We don't always have to draw the Q bar output on the schematic symbol unless we're using it, but be aware because of the way that we've built this, there's always a Q bar available, right? Because of it's built from an SR latch, right? Which is an SR latch, which is then combined with 2 extra NAND gates into a D latch, which then combine 2 of those and we get an D flip-flop. And so a reasonable question would be how many NAND gates is required to build a D flip-flop based on the architecture we know, right? We could calculate that out pretty easily. Okay, so first off, let's do the VHDL for the simplest part of this. To the SR latch. Okay, well, all I have to do here is I have 2 not OR gates, right? And if I call this signal A, this signal B, just for now, I can then say A gets assigned to not S or B. And B gets assigned to not R or A. Well, that still doesn't give me my Q, right? Because there's a quirk with VHDL that it really doesn't like it when you plug input output ports back into input ports, right? Because my input ports are R and here. So it's not going to like this. It does not like outputs on the right side of assignment statements. So what I do is I have little buffers. And what those buffers do is now on this side it's B, but on this side it's Q. And the definition of buffer is the output just equals the input. So Q gets assigned to B.
You know, wait, so would you still have the same thing for A?
Yeah, so Q bar gets assigned to A if I wanted that output accessible as well. There we go, we built an SR latch. Now, obviously, we're not gonna do this all of the time, right? We could describe all of our logic this way, but it turns out it gets easier rather than more difficult in order to design good logic from here. So
Is that Q minus?
Q sub, like Q sub, yeah, I don't know where to put my black one. Q sub B. Okay, so now, but we want to design something a little bit better, right? We want better code than that. And so let's talk about how we design a flip-flop, D flip-flop, let's say. And the way that this is going to happen is, remember how we've used processes in our test benches before? A process says that this portion of code is sequential logic. It happens in order. So we're going to start using processes inside of our design. So not just in our test bench, but we're going to design files with process. And we're going to say, and this happens just like in the test bench inside of the architectures begin. I say process. However, there's a difference right off the bat, which is the process is going to react to a particular signal. In this case, the clock. I want it to react to the clock. So I give a parentheses clock. This is called its sensitivity list. This is what signals cause the process to run. It's just going to sit there until one of those signals changes. In this case, clock is my only signal. It needs to begin. Again, if I was writing this in code, if I was writing this in VHDL, I would go write end process immediately because we know there's going to be an end process here. And if you forget them, the errors are terrible to hunt down. So if you ever write process begin, write end process and go back and fill in the remaining code. That's a nice helpful tip. Then, in order to react to only the rising edge of the clock, because right now it's going to run the process if the clock goes from 0 to 1 or 1 to 0. Well, they gave us this nice little bit of code that says, well, if rising edge clock, rising underscore edge, this is going to evaluate that if it finds a transition from 0 to 1 on the signal clock, then my output D gets assigned to, or sorry, my output Q gets assigned to my input D and if.
Following the same naming conventions as this, or?
As this. Okay. This is the device I'm building. So D, Q, so my output Q gets assigned to the input D when the clock changes from 0 to 1. We built that device. Now it turns out sometimes we want to reset a device. We want to forget what it was. So we can add, I'm going to have an active low reset. This is pretty common, a signal called reset, which needs me to rewrite the code. Now resets can be done two different ways. One of them is synchronous and one of them is asynchronous. Synchronous means that the reset must be active on the rising edge of the clock. Asynchronous says that it will react whether or not there's a rising edge of the clock, meaning that the reset is kind of more important. The reset is the most important thing, is basically what that means. So if I want to have a synchronous reset, meaning that it has to be synchronized to the clock in order to successfully reset, then all I have to do is modify this code just a little bit. I'm going to move the process up here. Process on clock. Begin. Well, I guess I didn't really need to do that. On rising edge of clock is really probably the best place to put this. Inside the rising edge of clock, if reset equals 0, 0 because I wanted to active low, then Q gets assigned to 0, else Q gets assigned to D. There we go, synchronous reset. However, I tend to design asynchronous resets most of the time because I don't like worrying about the timing of my reset. There are good reasons to use either synchronous or asynchronous depending on what your design is doing. Most of the time, asynchronous resets are completely fine. So if I want asynchronous reset inside of the process, I'm still going to do the same thing, but it's going to say if reset, oh, I do need to write the process, otherwise I will miss an important part. The process I want to run on clock or on reset, because I want the process to be able to respond to reset. That makes it asynchronous. Now I can say if reset is equal to 0, then Q gets assigned to 0, right? Reset. Else if, and this is an annoying thing about VHDL, the else if has no E, is else if. Be careful with that syntax. It's ELSIF, no space, no E. It's just a quirk of VHDL. Then Q gets assigned to, oh, if, and I'm going to start rising edge like this, RE. You cannot do this abbreviation in code, but on the whiteboard, it's going to save me a bunch of writing.
You should say begin at the top.
It should say begin. My VHDL on the whiteboard is never going to be perfect. I don't have a checker for me, right? And it's really easy to forget. Like I forgot the apostrophes here, right? We need the apostrophes if it's a bit, and we need quotations if it's a vector. Else if, right, and I forgot like the semicolon, something like that. If rising edge of clock, and RE is rising edge as written there. And if. There we go. That is an asynchronous reset because the process will react to the change in reset and do the queue. Now, there is something that you need to be very aware of that I often forget to teach, which is unfortunate, which is the order of your if statements matter. So over here on the rising edge, if I said, if rising edge of clock, if reset equals 1, then Q equals D, else if 0, that's probably okay because the reset condition is taken care of. But here, if I said, if rising edge of clock, then Q equals 1, else if reset equals 0, Q equals 0, that actually causes a problem because that's saying that the rising edge of clock would happen and evaluate Q and skip over the reset. Whichever if statement comes first, executes first. And if it sees the first one, it will just do that. So I saw some confused faces, so let me just draw. I have this type of code that has an if statement that conditions on two different signals, one N, one M. If N is 1 and M is 2, F is 7. Because it sees that, oh, N is 1, F is 7, we're done. Because this word is else if. If this is true, do that thing. If it's not true, move on. It's not going to do both because both are true. If you want it to do both, you need two separate if statements. So be careful with that. This is saying that if the reset is true, we don't care what the rising edge of the clock is doing, which is what we want, right? We just want it to be 0. If they're flipped, then it's saying if the rising edge of clock is happening, I don't care what the reset is doing, which is not what we want.
So this is the few times that order is important in VHDL.
Yes, order is important in sequential logic, right? Because it happens in order. It's this, then this, then this. That's the idea of sequential logic, is suddenly order matters. In combinational, it didn't, right? When we're doing combination, it only depended on the combination of the inputs. Order of your expressions didn't matter. Now it does. Okay. So sometimes we want some more functionality out of our devices. And so sometimes we want a device that has what's called a clock enable signal. And a clock enable says, I don't always want to care about what the data is doing. Sometimes I want to hold on, even if there's a rising edge of clock. I don't want to reset it. I don't want to make the data go away, but I want to remember this for a couple rising edges before I move on. How do we do that? Well, there's an obvious way. If I have a signal D, signal clock, and a signal CE for clock enable, with an AND gate, if clock CE, if CE is 0, doesn't matter what clock is doing. However, this is not the right way to do this. Does anyone see what the problem is? Does the clock input of my D flip-flop know the difference between the rising edge of a clock and the rising edge of clock enable? It doesn't. It has no idea which one caused it. So if my clock is over here doing this, right, and my clock enable does that, well, this rising edge of this clock does nothing because we're not enabled. But then the CE turns on here, and I get a rising edge of a clock in the middle of the clock, which is not really good, right? Because what's just happened is, well, we've created the output Q is going to do something like, well, not Q. Let's call that N, signal N. N is going to do something like this, where it's going to get a little flip in an otherwise good clock. The issue gets further exacerbated if the closer this gets to the edge of the end of this clock, because now it's going to do a little spike up, spike down, right? It's going to try and change to a 1, but it doesn't have enough time, so it's going to fall back to a 0. And now this triangle may or may not register. And if the signal is going to multiple flip-flops that have multiple clock enables, some of them might clock in the new data and some of them might not. And now they're randomly off because each of the devices are different. So that AND gate method is really hazardous to do, in fact, because now you have to have your clock enable synchronized. If you control your clock enable really carefully, everything's fine. However, there is a real potential for issue. So the right way of doing it clock Q this, which this is a mux with clock enable as its select signal. So now what happens is on the rising edge of the clock, if clock enable is 0, keep old Q. If clock enable is 1, bring in the new D. It will only ever update on the rising edge of the clock, but it's protected from seeing clock enable as a clock signal. Now you still have the potential for, you can't change clock enable at the same time as the clock. You still have some timing requirements there because you need the setup and hold times to be met. But this does give you a low level of protection that this one does not. So if I build that device, asynchronous reset, I can do this a couple different ways. But it's an if statement is fine, right? I can basically say on the clock and reset, if reset is 0, that makes it active low, then Q gets assigned to 0. Else if rising edge of clock, if rising edge of clock, and then I just have to say if CE equals 1, all right, equals, not assigned to, if CE is 1, which is going to take the new D, else Q gets assigned to Q. I tries to answer the clock. If CE is 1, get the new data, otherwise stay the same thing. This will weirdly build a mux. Even though we know that the when else statement is a good way to build a mux, the when else's don't work inside of a process because a when else is a combinational device. This will still build us the same device, it's just a different way of writing it. We have to be careful to understand that the way we write things changes what's happening. Now, this is an interesting point to make here, which is I've done if else versus else if. And there's a potential problem that we'll come back around and I'll emphasize more as we go on, which is in a programming language, if you're writing in Python or C, and you write the statement, if n equals 1, then f gets assigned to 7. And if this happens one time in a process, right, because the process is run over and over again, if that happens and n is 1, f will get assigned to 7. And then the process runs again and n isn't equal 1, f will still be 7 unless I've told it to be something else. However, you are not designing software here, you're designing hardware. What you've said here in Python is if n is 1, update 7 to f. In VHDL, in hardware, this says if n is 1, f gets assigned to 7, otherwise I don't care. I don't care what you do with f. Because it's going to try and simplify it for you. Now, the good news is that most of the time that simplification is stay the same thing, right? It takes very little effort to stay the same, and that is usually what happens. However, the more sophisticated your code gets, the more likely this will fail. So the technically correct one is else f stays f. We have to be very explicit in VHDL. I see these errors rarely in digital circuits in this class. I see them often pop up with actual issues in digital systems. So, but be aware that not having an else means don't care. I don't care what happens if I don't have that. In the case of the if reset else if rising edge of clock, you don't really need an else. It's fine. I've never seen this one go astray. I don't know, maybe I'll find something on the internet that tells me wrong and that I've been wrong this whole time in my career, but I haven't seen it cause an issue. However, the if statements when I'm assigning signals, I've seen cause issues fairly often. So be aware. Now we can also combine sequential and combinational logic in a design. Makes sense, right? We would want to do both at some point in time. So there's another device or another option where, in addition to a clock enable, I may want an output enable, right? This is just that tri-state buffer that we talked about a couple of weeks ago, which is if output enable is on, the buffer is connected, otherwise it goes to high Z, right? High impedance, it's disconnected. Well, the way that we do that is here, this is now Q, and this is QO for my output Q, okay? I come over here, I end my if, I end my process.
You have to end
Both ifs, I'm missing one. Okay, it's okay though, right? Here, there's another end if in there. Now I've ended the process, and now all I have to do is build the output enable device, the tri-state buffer, and that is simply as easy as going with a when else statement, it turns out. In fact, I'm going to bring it up here so it's easier for those in the back to see. So this is after the end process, but before the end of the architecture, right? We're still inside the architecture at this point. Now what I want is to say that Q output is going to be, well, Q when OE equals 1, else high impedance. Which is a mux, right? But it's just a mux that looks like that, where it's either connected to Q or to nothing, which is what we want, right? If our output's not enabled. So this is one way of combining output logic. This is the same kind of thing that we do, right? Because when I have this Q equals Q, I can't have Q as an output anyways. Because I put Q on the right side, I'm not allowed to have an output for Q. So I would need to create the signal QO anyways. I would just say QO equals Q, and I'd be done if I didn't want the output enable. Another thing that is worth noting is that a lot of times we build, like if we want to remember an 8-bit number, for example, I don't want to draw 8 D flip-flops. Turns out I don't have to. There we go. It's now 8. There's now 8 D flip-flops in that schematic symbol, right? Because one D flip-flop can't store more than 1 bit. So if I write the bus /8 saying that the bus size is 8 now, it implies that there must be 8 flip-flops. Once we start having those together, we call them a register. So that's going to be vocabulary that's going to pop up soon. In fact, we're going to build a very simple register in project 2 that's going to attach to your ALU so that it can remember the values that it started adding together. Don't worry, I fully expect they have to go back and review all of this, right? Because we're gonna have like one more class Thursday, and then you're gonna not see me for a week and something. So we're all gonna forget everything. So we'll come back and review. But there is one more device. It's basically one more device that we need to talk about, which is basically the same concept as the D flip-flop or the SR latch, but instead we call it the JK flip-flop. And it looks like so. And what the JK does is the following, where I have inputs JK, and this is going to be the next Q. And in this case, the n+1 is the number of clocks, right? This is really where this notation comes from, which is discrete mathematics, which is the next Q, the next time there's a rising edge of clock. What is it? Well, if J and K are 0, 0, just like the SR, these are actually very close to SR. They're related to it in some way, which is to say that stay the same. If they're 0, 0, reset on K, set on J, but then it gives us something to do with the 1, 1, which is rather than it's bad, it inverts. Whatever, if Q used to be 1 and I put 1, 1 on my JK, I get 0. It inverts. There's a similar functionality, which is really nice, which is if you take both of the inputs and tie them together, like so, that makes a new device. Called a T flip-flop. A T flip-flop is a toggle flip-flop, because if T is 0, Q stays the same. If T is 1, it toggles, it inverts, right? Because it's just this row or that row. It can't be the middle two because they're tied together. So it's either toggling or not. It turns out that coming up next time, we'll get into it using these toggle flip-flops. I can basically just start stringing them together and building counters. This is how we start counting in the easiest way possible, which is where we're heading. I still have like 4 minutes, so I'm going to go ahead and pull another example. We're going to do another timing diagram. We're going to do one of the harder ones. Let's go ahead and do a JK flip-flop. All right, clock's a little screwy, but it should be okay. So the nice thing is, once I know that it's a JK flip-flop, it's rising edge triggered, let's say, then I can just go ahead and say, well, what is Q doing? Well, in the beginning, J is 1, K is 0. But I don't have a rising edge of a clock. That's another way of saying, unless you have an assumption, it is until there's a rising edge, I don't know. I don't know what it is. But once I've done that, There's a rising edge. J is 1, K is 1. I invert. What's the inverse of I don't know? I don't know. Okay, I've got another rising edge. Now I've got J is 0 and K is 1. Well, if I look over here, K is 1, that's reset. Now I have a value 0, right? Which is to say 0. This rising edge of the clock is the other way. Oh, wait, nope, 1, 0. Still 0. Oh, wait, J is 1. Never mind, it inverts, it does. Well, not inverts, it sets to 1. There we go. All right, that one got droopy. So I'm just looking for the rising edges and I'm setting them based on the value. If it's trying to, if you don't know, put X, right? If it hasn't been set to anything. Sometimes in the questions I'll say, assume it starts at 0, in which case we could, right? If it started at 0 and then we toggled, it would go from 0 to 1. Which is to say, I can draw that. If I said, assume Q starts at 0, well then when I did this and I have 1, 1, now I toggle. And then when I have the next rising edge is still set to 0. If this were a falling edge device, instead of caring about the rising edge, I start caring about what the falling edges are doing. And let's say I do the same thing and I say I assume it starts at 0, it reaches its first falling edge, and see how those change at the same time? I don't meet setup and hold times. It means, I don't know. Now there's a falling edge with a 0, 1, J being the 0 or 0. So be very careful with the setup and hold times. Make sure that you know what it's supposed to be. Anyways, that's time so you guys can run away and do everything. I'll post the homework that's going to be mostly, I think, timing diagrams for flip-flops just to get latches and flip-flops, right? Latches react, they're combination. Latches are essentially combinational devices because they respond immediately with a small delay to the changes of the input. Flip-flops are clocked. There will be a clock in the timing diagram when you do it. Look for whether it's rising or falling edge triggered. That's all that's the bulk of the homework. You might have to write a little bit of VHDL for some of these modules.
For our homework today, do you want screenshots or do you want to just copy and paste it on that?
Screenshots are fine.
He's actually have to install the HDL.
You can go in the lab, or you can use EDA Playground if you want to figure that out.
I'm not gonna do that. They're fun, but we'll see. Very down low.